Okay, we are going to discuss the first law of thermodynamics now. Specifically, we're going to come up with an expression for work. We're going to talk a bit more about work's role in thermodynamics, and come up with the first law of thermodynamics, and then discuss a few applications of this law. To start, let's look at some important definitions that we'll need to know when discussing the first law of thermodynamics. So a thermodynamic system is the complete set of thermodynamic objects under consideration. Okay, and that can be any type of object. There's a number of different ways we can define it, and one of the most common examples of this is the universe. The universe is a large thermodynamic system, okay, and that is what's known as a closed system, which means nothing can get in and nothing can get out. Okay, so an example of an open system is one where mass can get in or out. So an open system would be a container with a gas inside, and that's open to the outside world. So gas that is inside or outside can get in and out. So this gas can leave, gas on the outside can come in. Whereas a closed system is one in which there is gas inside a closed box, and that box would be thermally insulated. So it would be kept at a constant temperature, okay, and is insulated from the outside world. So no heat can get in. There's nothing externally that can change the internal dynamics of this system. The volume or pressure of this system may change, okay, but it is thermally insulated. It's completely separate from the outside world. And that is an example of a closed system. Okay, so these are two important concepts that'll come up quite frequently. Another one is the state of a system. And the state is the set of all quantitative parameters that define a thermodynamic system. Okay, so what are some examples of those thermodynamic parameters? Well, as an example, we can have a gas with given pressure, volume, and temperature. Okay, and so any examples that give these give these variables will be examples of the state of a system. Okay, so if a metal with a given volume and a given temperature expands to a new volume, that temperature will change. These are all states of the system, and they are all needed to define the overall state that a thermodynamic system is. So define everything that comes with that thermodynamic system. Okay, so now that we have a few of those definitions, let's talk about the work, which is going to get us one step closer to defining the first law of thermodynamics. So work, by definition, is defined, if we think back, work is defined as F, the force, external force applied on an object, times the displacement that object incurs. Okay, so this is the definition of the work. Now let's say that we are exerting a force on a gas via a frictionless piston. Okay, so the piston, there's a pressure that comes down. This piston has a cross-sectional area of A, and it is displaced a distance delta x. Now, by the definition of work, we know that the change in work will be the force. Now, this is a constant pressure pushing down, so let's say a constant force times the displacement. Okay, and we know that force is defined as, let me backtrack. Pressure is defined as force over area, because we know that a pressure is going down. Well, that's related to force via the force over area. And so force then is defined as pressure times the cross-sectional area, and this is all multiplied by delta x. Now if we put the cross-sectional area and the displacement together, all right, the cross-sectional area times this distance, well, that defines a three-dimensional volume. And so the work is P times delta V. And so that's the definition of change of work from a thermodynamic perspective. Okay. So we want to use that because this is going to be very important. We're going to see examples of this, but as we can see here, it's a useful idea to define work as pressure times volume, because these both define the state of a thermodynamic system, the pressure and the volume, as well as the temperature. Okay, and so we can look at pressure and volume graph. Now, what we could do is have a three-dimensional view of all of the states, all of these states of a thermodynamic system. And so we could have the volume, the pressure, and the temperature. And the contours within this three-dimensional surface will show us what state that thermodynamic system is in. Okay, so in this example, we have the pressure and volume like this. Well, this would be kind of a three-dimensional surface, just like this. My drawing is bad, I apologize for that, but basically a three-dimensional contour where the temperature is constant on that point, okay? So pressure, volume, temperature gives us a way of defining that in 2 dimensions. So, as an example, now if we were to, this is a constant pressure. Now if we extend this a little bit to this situation where the pressure is not constant, okay, so the volume changes by some amount because a changing pressure is forced onto that piston, which changes the volume in a way that would be hard to define. Now, if it changes in this manner, which we're going to discuss a little bit later, okay, the work is just P times V, which is just the area of this. So it's pressure times delta volume, delta volume, the change in volume. Now, if the pressure is constantly changing, we need to use calculus to define this, because we want it to be the area under the curve. And so if you're familiar with integral calculus, you would know that, you will recognize that taking the integral from a to b of P dV will actually tell you the work under this, the work done by this moving piston. Okay? So let's try an example of this. A gas is compressed at a constant pressure from a volume of 2 meters cubed to a volume of 0.500 meters cubed. So volume is 2.00 meters cubed. Volume 2 is 0.500 meters cubed. What is the work done? So this is question number 1. What is the work done? Well, work is, we know that change in work is P delta V. Now P is constant, delta V changes, and so this is 2.0 times 10 to the 3 pascals times the change in volume. And the change in volume, this gas starts at a volume of 2 meters cubed and is reduced to 0.5 meters cubed. And so the change in volume is just 1.50 times 10. Oh, excuse me. Let's go back. It's just 1.5 meters cubed. Let's get this erased. There we go. So 1.5 meters cubed, which gives us work done of 3.0 times 10 to the 3 joules when we multiply those two numbers together. The second question gives us a bit more information. And so if the temperature was initially 40 degrees Celsius, what is the final temperature of the gas? And so this brings us back to using the equation of state. Now we know that there's a change in volume, and corresponding with this change of volume, there's a change in temperature as the pressure remains constant. And so the ratio of volume to temperature, we know from looking at the equation of state of an ideal gas, is V over T is constant. Another way of writing that is V1 over T1, this ratio, is exactly equal to V2 over T2. And so if we substitute in our known values, 2.00 over T1, and so that temperature in degrees Kelvin is 313. I'll just put units in here. 313 Kelvin, whenever using an equation of state, should always be in degrees Kelvin, meters cubed, and pascals, or and Pascal, yes. So volume now is, it changes to 0.500 meters cubed divided by T2. All right, and you need to rearrange this equation. So the T2 will come up here. You're going to be left with 0.50 multiplied by 313 Kelvin divided by 2.00 meters cubed. So I want you to try that on your own, rearrange that equation, and the final answer you should get is 78.25 Kelvin. And if we convert that back to Celsius, which is what we were originally given, this gives us a temperature of minus 195 degrees Celsius. So quite cold. Okay, and to help us understand this a bit better, we can look at the equation of state of an ideal gas. PV equals nRT. The volume is going to decrease, so this gas gets compressed. So that means the volume is lowered. Okay, if this side of the equation decreases, this side must also decrease, which means the temperature should also decrease. And so we saw a temperature decrease from the initial temperature, so this is exactly what we expect to happen. Okay, so that is a little bit about the work done by the gas and an introduction. Next, we're going to look at a bit more about pressure-volume diagrams, and we're going to get into the first law of thermodynamics.